Hello. Today I'm going to discuss homework 3. So, especially like homework 3, question 3, I mean, it's maximum likelihood estimator for binary distribution. And most of you have done well. So, but like few students have paid attention to this thing. And you may have guessed this is used to show this. Okay, so let me explain what I have seen from your answers. First, like these three questions uh, is really easy. So you may have wondered why you have to show this. It is obvious. I understand that is obvious, but when you know the answer, they are obvious. But several years ago, I did not have these parts, and then many students struggled from here, right? So like several years ago, I started from here, then then they didn't know how to handle. So that's why I included these three questions. And so please understand, even if it's too obvious, it's to guide you, right? Guide you through those steps. And as you could see from the following questions, what I tell you usually is pretty basic. There's nothing new. Usually, okay, let me continue. I will explain. So ABC was easy. And part D, let's look at the part D. So it is to show that uh, this parameter is the unique maximizer of the objective function. You know how to do this. You can check the first order condition and then the second order condition. So it should be easy. But what I want to recap here is notation again. So this is the first derivative of the objective function, which is defined as you can change the order of expectation and derivative. Um, and then after some simple algebra, I believe you could show this. But here, note that it is P and this is P because this is argument, just general argument. And so you have to differentiate with respect to the argument. And so this is P because we evaluate that at a P. Like you can, so if you used a different notation like P0 here, this should be P0 here. But I leave it as P because it is just another function, first derivative function. So its argument is P again. But earlier we defined P0 as the expectation. So the derivative has an expectation. So some of you replaced this expectation with P0. This is correct. And this will be replaced by 1 minus P0, right? So like from here, you have to be careful because in this function, you have P and P0 at the same time. So P0 is specific, the true value, and this denominator P is the argument of the function, right? This denominator can take different value, any value between 0 and 1. So this is just, it is a function with respect to this guy and this guy, okay? So these two guys are variable. They are changing, and the numerator P0 is simply just the expectation, which is constant, which is true value, okay? And then this is the first derivative, and from here you show that you want to find the solution that makes this derivative equals to 0, right? So, and as a result, you have to solve for that equality for this P, these two denominator P, right? So as a result, the variable P should equal to P0 for this to be 0, right? That is how you proceed here. So different notation for different purpose. And if you were confused, then what I recommend is just keep expectation as an expectation, right? And in the end, you just want to show that the solution is P equals the expectation. That would be the same thing, right? Uh, but of course, the convention is starting with P0 usually, but it does not matter even if you do not use the P0 notation. Not a problem. Okay, let's go to part H. So all the other parts are easy. So you have done well, except for minor things. Okay, these are not much a problem. But let's go to this bounding, right? So let's think about the bound here. It's simple, like it's scalar, so it should be simple. So first, let me explain this first. If you want to show that A is bounded for any value of P, so what we want to do here is supremum of P. So take supremum over P, like this is a function of P, and you take supremum over P. So choose the P that maximizes this value. Okay, so this is like this. Want to show that A is bounded over P. And then mathematically what it means is just its definition is to find a constant that does not depend on P, but the absolute value of A is bounded by C for any P, right? So then this is the bound. For whatever P is, anyhow, A will be bounded by C, right? Of course, C should not depend on P. So think about this definition, right? So we are looking for this thing. We need to find something that does not depend on P, but create a bound A, right? Bound the absolute value of A. And in this question, let me start with the second derivative first because it is actually easier. We are going to bound this, and you know the second derivative looks like this, and actually uh, its absolute value takes this form because we know this is positive, this is positive, this is positive, this is positive. I mean, this is 0 or 1, this is 0 or 1, and positive, positive. So it is easy. You may use like triangular inequality to keep the absolute value here and here, but in the end, you are going to get this. Okay, so I believe it should be up to this. It's simple because everything is positive. There originally you have to have minus sign here and here, but they go away because you make everything positive. And then denominator P will be bounded by 1 over P will be bounded by 1 over C because we assumed this, right? So of course, it's the notation here is not perfect because this P should be restricted to this interval, right? So under this assumption, it is obvious P squared, 1 over P squared will be bounded by 1 over C squared. Similarly, 1 minus P squared, like 1 over 1 minus P squared will be bounded by 1 minus 1 over 1 minus C squared. So I believe it should be straightforward. Okay, and then right hand side, this is what we want. Right hand side is independent of P. P disappeared. So originally we started from a function of P, second derivative of P, but in the end, right hand side, we bounded using something that does not depend on P, right? Exactly, this is this C here. However, it is still random because X is random. So you can understand it like this. X is random. So for a realization of X, for any realization of X, you are going to bound that by this, right? This inequality holds for any value of X, for any value of P, right? So then, so from here, because it does not depend on P, So you can, like, this is more correct notation. You can bound this guy, second derivative, like this, exactly as I said. So supremum is bounded by this. And so now, as I said, it is still random. This is random. So if you take expectation on both sides, right, you are going to get this expectation on the right hand side. Okay, right? So, and then this is a clear constant. It is a constant. It is not random. It is a constant, so it is obviously bounded, right? Okay, this is the a good example how to bound, how to find a bound mathematically. Now I'm going to bound the original like a log likelihood function. So, but like it is tricky, but it is not that difficult. It is nothing new. Very basic elementary mathematics. So first, like think about a if a something is less than one, then log of a is less than zero, right? Log of one is zero, so log of something less than one is less than like is negative. And also, log of a will diverge to the negative infinity as a converges to zero. So what you have to worry about is, so if log of a is not bounded, then that's because it goes to minus infinity, not to the positive infinity. So you have to worry about it is bounded from minus infinity. That is what you have to show, because upside is obviously bounded by zero, right? So upside is clearly bounded. So the problem is the downside. Downside uh, should be bounded. So most of you just argued like this, right? Log of p is less than constant, or did not explain how to bound it. But it's wrong. It does not bound the log correctly because it is negative. So bound from the positive side is nothing. Like doesn't mean anything here. And here comes our assumption C and 1 minus C. That is because we can show that P is greater than or equal to C, which is positive, and also it is bounded above from 1 minus C, less than 1. Then you can bound from below, like log of P is bounded from below by this guy, and log of 1 minus P is bounded from below from by the same guy. So then this is a constant that we are looking for, right? So you have to utilize these guys to bound something, right? So more formally, you may write this way. So because these are, we know these are strictly negative, I'm going to choose a constant c such that it's a c equals minus log of lowercase c, right? This c, right? Because we are going to bound from below. So because it is also negative, so I will put minus here so that we have like a positive constant here, and then you are going to get this bound. Like so, absolute value is minus of log p, right? So if you think it more carefully, this is obvious. Log of p is minus, so you have to put minus. So like bounded by this guy, minus of log p. Okay. Um, Finally, I want to mention this. I'm not sure if you have thought about this. Earlier, in a previous part, we have proved that P0 is the P0 maximizes this guy, right? Which means, so which means P0, if you plug in P0, that is a supremum of this guy. But this is different from what we are doing in here, in bound, because mathematically this equality does not hold, right? So earlier we maximize this, but now we take maximization first and then take expectation. The order is important, like taking expectation first and then maximization is the MLE estimator, but taking maximum first and then taking expectation is totally different. You have to discuss if it is well defined or not. Okay. Okay. Good job. Thank you for watching.